Hi, my name is Povi Batula, and this is Lab 03, Black Hole in Orbits. This lab is split into two parts. For part one, the purpose is to determine the average mass of the black hole, and then part two, you determine the initial velocity of the moon's orbital speed and simulated orbit of the moon and orbit of a spaceship without it crashing to either a moon or a planet. So overall, this lab will demonstrate the effects of Newton's second law and its relationship with momentum, and the overall result is a average mass and a So the fundamental physics involved are Newton's second law, gravitational force, centripetal force, and it all results into circular motion. So Newton's second law is change of momentum over change in time, and we equate that to F net, and F net can be broken down to parallel perpendicular components. Perpendicular component is mv squared over r, and that itself is the centripetal force. And we use Fg, which is the gravitational force, because we're dealing with large objects as our system, and they have large forces between them, and we need to take that into account in our calculations. Part 1. So the system is a star, and our surroundings is a black hole, and in our initial conditions, we have something called C, which is the iterative step that we are using in our calculation loop. We have a gravitational constant, we have the mass of the star, and we have a delta time stamp. So in our calculation loop, we have our initial and final velocities. Same with our initial and final momentums, and we calculate delta V and delta P, and we use delta P over delta T to calculate F net, and this is circular motion, so we break down F net into perpendicular and parallel components. And of course, this is important as we need to find the mass of the black hole, and we take F net to be the result of our gravitational force, and we rearrange the equation of the gravitational force to find the unknown, which is the mass of our black hole, and you see that equation in our calculation loop. So as a result, we have a net force, we have its parallel and perpendicular component, and we also have the average mass of the black hole. And this is an iterative calculation, so obviously as we calculate through, we have a average mass of the black hole. So part 2. So the system and surroundings are interchangeably calculated, and we can see that in calculation loop in a little bit. So in our initial conditions, we include the inputs of our gravitational force, the mass of the planet, the mass of the ship, we have our delta T, and we calculated for the initial moon speed and its velocity. We also calculated its orbital period, and notice that we use the circumference of the moon, and we have it divided by speed and then time. In our calculation loop, we calculate the gravitational force between the planet, ship, and moon, and the systems and surroundings constantly change, and then we applied Newton's second law, the velocity update formula, and the position update formula for the moon and the ship. So as a result, in pink, that is the orbit and path of the ship, and in blue, that is the orbit of the moon. It is nice to know that we have a nice little circle orbit for our moon, and it looks a little crazy for our ship, however, but this is computational and experimental, and it helps us to grow and learn. So possible errors that you can have are approximations and accuracy. Since this is a simulation, it may not always represent reality, and we're assuming that there are no other outside forces acting on the system, and this is where the differences between an observed data set, if we had one, and a computational data set occurs. The calculations for computational are much more precise, but many factors are left out. Now, when it comes to accuracy, trial and error was used to find velocities. There could be much more precise velocities that will allow the spaceship to get closer to the planet. So let's ask ourselves, how is the net force and its parallel perpendicular components different from the rate of change of momentum and its components? So computationally, they are the same, and the difficulty lies in the rate of the measurement. The net force, all and every individual outside force must be accounted for. However, in the rate of change of momentum, it's more an internal thing. The system's change in velocity and motion are accounted for. So now, if we wanted to predict the motion of the entire system, what needs to be included? So we need to include all the gravitational interactions of the planet, moon, and spaceship, and we also would probably be better off if we added relativistic effects, non-spherical planet data points, and of course energy conservation. Now, would there be dominant interactions? The dominant interactions would be the gravitational forces between the planet and the moon, and the planet and the spaceship. The mass of the planet makes it such a main influence on the moon's orbit, and the spaceship's influence on the moon is much weaker unless the spaceship gets really close to it, so the main interaction between the planet and the moon will govern the entire system's behavior. So in conclusion, the development of the computational model for circular motion definitely involved a lot of trial and error, and each iteration defined accuracy, but overall I was able to gain a deeper understanding of the forces of play during circular motion. Thank you.